sections are curves that are formed when you slice a cone with a plane. There are actually four conic sections: the parabola, the ellipse, the circle, and the hyperbola. Each of these conic sections have a huge application in real-life situations. Parabolas, when we have a spun parabola to do 3D and have the focus be where we have a receiver, or like our satellite dishes. With ellipses, those are actually the paths that the planets take when they go around the sun. Hyperbolas and our circles also have a huge number of applications, and this video is designated as concentrating on specifically the hyperbola. For my other videos on conic sections, I've given you links in the description of this video to go back and look at those components. Now, with a hyperbola, it is defined to be a conic section in which the differences of the distances from two fixed points to any point on the curve is a constant. Those two fixed points are what are called the foci of the hyperbola. Now, our hyperbola actually are what you get when you have a cone and then another cone, they're tip to tip, and you take a slice with the plane. So you get a hyperbola at the top and at the bottom, or if you have them side by side, you get the hyperbolas going this way. Now, if you have your transverse axis to be horizontal, so you're holding the cones tip to tip horizontally, then the equation is x minus h quantity squared over a squared minus y minus k quantity squared over b squared is equal to 1. And the picture looks like this. So our transverse axis is horizontal. That transverse axis is the axis that our vertices and our foci are on. And in a hyperbola, the distance between the center and the vertex is a. The distance between the center and the vertex, even on an ellipse, we denoted a, so that's consistent with that idea. And the distance between the center and the foci is c. The biggest difference here is that c is larger than a when we have a hyperbola, and c was smaller than a when we had an ellipse. Now, also, we have asymptotes for a hyperbola, and our two asymptotes, if our transverse axis is horizontal, are y minus k is equal to b over a times x minus h for one of them, and the other one is y minus k is equal to the opposite of b over a times x minus h for the other one. And these asymptotes are actually the lines, the asymptotes, that go through the center and the ends of the hyperbola are attracted to. Now, when you think about the idea of C and A being A, the distance from the center to the vertex, and then C being the distance from the center to the foci, but in our equation we've got A squares and B squareds. Well, there's a relationship between the a squared, b squared, and c squared. And for a hyperbola, that relationship is that b squared is equal to c squared minus a squared. Now again, that makes sense, because in a hyperbola, c is bigger than a, so the square of c is going to be bigger than the square of a, and I have to get a positive number out of this because my b squared is what it's equal to, and the square of a real number has to equal a positive number. Also, when I look at this, that means that there's this value of b that we haven't actually put on the diagram. Well, b is the span from the center up to what would have been like edges on what's called the fundamental rectangle. So if I go b up from the center, if my transverse axis is horizontal, and be down from the center with that transverse axis being horizontal, then making a rectangle that goes through the vertices and also goes through these points that we get B above and B below the center, this rectangle is called the fundamental rectangle. And actually these asymptotes go through the corners of the fundamental rectangle. They're the extensions of the diagonals of the fundamental rectangle. So I can actually get those to help me graph the hyperbola a little bit better. So I have the correct shape of the curvature of it. Now the fundamental rectangle then is A and A 2A wide and B 2B tall. So 2A times 2B gives me 4AB as the area of my fundamental rectangle. Now lastly with information is the eccentricity. Eccentricity is defined to be our C over A, and our eccentricity is greater than 1 when we have a hyperbola, which again makes sense. C is bigger than A. So if I have a larger number in the numerator than I have in the denominator, I will get a number that's greater than 1. Now just kind of to quickly go over the specifics if our transverse axis is vertical. So if our transverse axis is vertical, it's y minus k squared over a squared minus x minus h squared over b squared is equal to 1. And with the hyperbola, it's important to notice that your a squared, once you've got 1 on the right hand side and you have coefficients of 1 in front of your x minus h and in front of your y minus k, then the a squared is always the number that's under the positive fraction, and your b squared is the other number, the other denominator. Now if you recall or look back at the ellipse, once I had it equal to 1 and my coefficients were 1 in front of my x minus h quantity squared and my y minus k quantity squared, my a squared was the bigger denominator. That's the ellipse. For the hyperbola, my a squared is always the one that's under the positive fraction. Now, for our transverse axis being vertical, again, it's y minus k quantity squared over a squared minus x minus h quantity squared over b squared is equal to 1. My asymptotes are y minus k equal a over b times x minus h, and y minus k equal the opposite of a over b times x minus h. And this is what the diagram looks like. And with this then, my transverse axis is being vertical. My vertices are above and below the center. My foci are still above and below the center as well as the vertices. And if I find the b value here, you're going to get your fundamental rectangle. You can extend the diagonals for your asymptotes, and then that gives us the diagram. Okay, so now let's look at some examples. For this example, it's asking us to find the vertices, foci, eccentricity, and area of the fundamental rectangle for 25y squared minus 16x squared plus 100y plus 96x minus 444 equals 0. Well, I want to write it in either my x minus h quantity squared over a squared minus y minus k quantity squared over b squared equal 1, or with the fractions reversed in order to find all of these pieces. And what we need to do to get started is we need to complete the square on these quantities so that we can get our binomial quantity squared to find our center, and then build off of that to get our vertices and our foci. So we're going to start by writing the terms that have the same letter in them next to each other. So I'll do the 25y squared plus 100y, leave space for completing the square, then minus 16x squared plus 96x equals, and we're going to add that 444 to the other side. Now, to complete the square, we need a coefficient of 1 in front of our square term. So for each of these, we're going to factor out whatever the coefficient of the first term is for the terms with the same letter. So we're going to factor out a 25, and that leaves me with y squared plus 4y. Leave the space, close your parentheses. Now here I'm going to have to factor out a negative 16, So be very careful to not only factor out the number, but the sign that you need to as well. So write negative 16 times x squared, and then plus 96 divided by negative 16. Well, positive divided by negative is a negative, and 96 divided by 16 is 6x, and then equals 444. Now complete the square in the parentheses, and then remember you're completing the square on what was in here, but you have to compensate for how you've really affected that side by doing that process. So complete the square, take half the middle coefficient. 1/2 of 4 is 2. 2 squared is 4. So I'm going to add a 4 in here. But that changed that side, not by 4. It changed it by 25 times 4, or 100. So I'm going to also have to add 100 over here. Next, complete the square on the x's. 1/2 of negative 6 is equal to negative 3. Negative 3 squared is positive 9. So we're going to add a 9 in here. But then I didn't change that side by 9. I changed that side by negative 16 times 9. Negative 16 times 9, we get negative 144. So I have to subtract a 144. And then factor your perfect square trinomials. Y squared plus 4y plus 4, well, that factors as y plus 2 quantity squared. And that wasn't a hard one to factor, but a good thing always to know is that factorization for your what binomial quantity squared gives you that perfect square trinomial. This number in here is always whatever half the middle was, and take care to take the sign with it, and then that helps you a lot if you've got a problem that's got fractions in it. Your number term in here is always whatever half the middle was. So now this is minus 16 times x squared minus 6x plus 9 factored. Well, half of my negative 6 is negative 3, so it's x minus 3 quantity squared. And on the right-hand side, we are going to combine our like terms. So 444 plus 100 is 544. Subtract 144, you get 400. Now what we're going to do is realize that we need to have a 1 over there. And since we need to have a 1 over there, we're going to divide both sides by this 400. So divide both sides by 400. Now, I'm fortunate here that my common factor of 25 is going to remove, and I'll get a coefficient of 1 in front of my binomial quantity squared in the numerator just by removing common factors. If that weren't the case, I would need to flip that back down and get whatever number would be in the denominator that would still give me a 1 as a coefficient in front of my binomial quantity squared in each of these cases. But we have it where if I take 25 goes into 416 times, so I have y plus 2 quantity squared over 16 minus, and then 16 goes into 425 times, is equal to 1. Now I'm ready to identify the different pieces. First of all, our center is your x coordinate always goes with your x letter, and your y coordinate always goes with your y letter. And remember, it was x minus h and y minus k, so it's what follows the minus. So I'm going to have an x coordinate of 3, and you can also think of it as what x would be plugged in that would give that a 0 out. So an x coordinate of 3 and a y coordinate of negative 2. So that's my center. My fraction that has a positive in front of it once I did all of the process is this fraction that has a 16 in the denominator. So a squared is 16 and b squared is 25. Now remember, in the ellipse, your a squared was the bigger denominator. In a hyperbola, a squared is the number that's under the fraction that's positive. Okay, then our relationship, remember, was b squared is equal to c squared minus a squared for a hyperbola. So we have 25 is equal to c squared minus 16. Add the 16 over, I get 41 is equal to c squared. So c is equal to the square root of 41. And now that we have all of that, we're ready to answer our questions. Now the fraction that was positive is the letter y, and when it's the letter y, your transverse axis is vertical. So we can kind of think of it here, our transverse axis is vertical. We have a center at 3, negative 2. So I'll just mark that here that that's 3, negative 2. And then I have my a value is 4. So to get to the vertices, I'm going to have to, from this point, go 4 up and 4 down. Now, going up and down off of a point is going to change its y-coordinate, not its x-coordinate. So when I add 4 to the y-coordinate of negative 2, I get a point, positive 2. And when I subtract 4 off of the y-coordinate, I get a point that is 3, negative 6. So those are my vertices. My foci are add and subtract c from your center. And again, because we're going vertically, we're going to have our foci at 3, but my c is the square root of 41. So to add the square root of 41 to negative 2 and leave it exact, I'm going to actually write negative 2 plus the square root of 41. And then my other one is at 3, negative 2 minus the square root of 41. And so we have our hyperbola looking like this. And so far we have the information for our vertices, for our foci. Our eccentricity E is equal to c over a, the square root of 41 over 4. And then the area of the fundamental rectangle is 4 times a, which is 4, times b, which is 5. So when I take 4 times 4 times 5, I get an area of a fundamental rectangle of 80 square units. So this gives me all of our information. Our center, our vertices, our foci, our eccentricity, and our area of our fundamental rectangle. Next, let's look at an example where they give me information about the hyperbola and I'm to come up with the equation. So here it says, find the equation of the hyperbola with the vertices of negative 3, 2, 5, 2, and foci at negative 4, 2, and 6, 2. So I know that I've got two different forms depending on whether the transverse axis is horizontal or whether the transverse axis is vertical. I also know that the key pieces of information I really need are A, B, and then my center, HK. And then I can just plug that in and get my equation. Well, all of that is actually embedded within my points here, and to get a visualization of it, it's always great to just plot out your points and then see which case you have. So if I look at just plotting these points out, I have negative 3, 2 is a vertice, 5, 2 is another vertice. So now I'm seeing that my transverse axis is horizontal. Then -4, 2 is a foci, and then 6, 2 is a foci. So since my transverse axis is horizontal, I know it's the x minus h quantity squared over a squared minus y minus k quantity squared over b squared is equal to 1 case. Now, h and k is the center, and the center of the hyperbola is on the transverse axis, and it's actually the midpoint between either the two foci or the midpoint between the two vertices. It's the same point, whether I do the foci or whether I do the vertices. So if I look at the midpoint of these points, say I'm going to take the vertices just because they're listed first there. Remember, the midpoint is the point that if you add the x coordinates of the 2 points and divide by 2, that's your x coordinate of your midpoint. So you're just averaging the x's to get the x coordinate of your midpoint, and you're averaging the y's to get the midpoint, the y coordinate of the midpoint. So here, if I'm using the vertices, I'm just going to denote this for the time being to plug everything through so you can follow along and see what we're doing. So x sub 1 is -3, x sub 2 is 5, and then y sub 1 is 2, and y sub 2 is also 2. So this gives me -3 plus 5 is 2 over 2, which gives me 1 as my x coordinate of my midpoint, and 2 plus 2 is 4, and 4 divided by 2 is 2. So my midpoint's 1, 2, so my center's 1, 2. And even if I would have done that with the foci, so -4 plus 6 is 2 divided by 2 gives me 1, and 2 plus 2 is 4 divided by 2 gives me 2. So right now my h is 1, and my k is 2. Now, what about the a squared and the b squared? Well, remember, a is the distance between the center and your vertex. So, since my center is at 1, 2, and this vertex that's to the right of it is at 5, 2, the distance between these 2 points is a distance of 4 units. So, a is 4, which means a squared is 16. Now to get the b squared, well, I know the relationship in a hyperbola is b squared is equal to c squared minus a squared. So b squared is equal to, well, c is the distance from my center to my foci, and this foci is 6, 2. So then my distance there is 5. So c is 5, meaning that c squared is 25. So I have b squared is equal to 25 minus 16. So b squared is equal to 9. And this then is the equation of the hyperbola